All right, hey guys, welcome to our first flipped classroom lesson on stoichiometry. We're going to talk about mole ratios. So stoichiometry sounds like this big scary word, but really it's just a term that we use to describe calculations to determine the quantities of both reactants and products across some chemical reaction. These calculations are always going to begin with an amount of one of our substances in that chemical reaction and ask you to determine the amount of another substance that's in the same equation. So for this reaction we've got nitrogen gas reacting with hydrogen and giving us ammonia gas. We're going to use these coefficients in a balanced chemical equation to help us. So we can figure out a few things through this one equation that's balanced. We could figure out the amount of ammonia that would be produced if we were given a specific amount of nitrogen. We could also figure out the amount of hydrogen that we need to produce a certain amount of ammonia. And we could use the amount of nitrogen needed to react with a certain amount of hydrogen. So you can think of this kind of like a recipe. In a recipe, say you wanted to produce a certain amount of, fajitas. You need a certain amount of chicken, vegetables, etc. Same idea here. All right, so let's start with something simple, something everyone can relate to, a tricycle. We all know what a tricycle looks like. Typically, it's got a frame, denoted with an F here, a seat, 3 wheels, a handlebar, 2 pedals, and this is our chemical formula for our trike for this example. All right? So, if you worked in a bicycle factory and you needed to make 100 tricycles, how many pedals would you need? So think about it for a second. It's pretty logical. 100 tricycles, 2 pedals per tricycle. You need about 200. You need exactly 200 pedals. You knew that just through logic, right? By comparing total tricycle to number of pedals needed. What about if you're given 200 pedals? How many wheels would you need? You would need, 300 wheels, right? You know that because for every 2 pedals, there are 3 wheels. You can see that up here as well. But for this example, this is just very common sense. So what these are ratios, right? You see them in math. We're comparing one item to another item and the amounts of each. So ratios are the same thing as conversion factors. Yes, we've used those in the beginning of the year. We're bringing them back. A classic one would be 12 inches to 1 foot, right? Conversion factor ratios, that's the same thing. For this example, we could say that for every 2 pedals, we have 1 trike. Same thing. 2 pedals, 1 trike. We could also flip that ratio to have the 1 trike to 2 pedals. We also have the ratio of 3 wheels for every 2 pedals. 3 wheels for 2 pedals. We can write these opposite, just like we can write 12 inches, 1 foot, to 1 foot, 12 inches. All right. So we're going to use these ratios to help us solve chemical problems. So let's use a real example. All right. So coefficients in balanced equations have many different meanings. They're very important. This is why we balance equations. So if we're given this same example, nitrogen gas plus hydrogen gas gives us ammonia gas, pay attention to those coefficients. They can mean that we have 1 molecule of nitrogen reacting with 3 molecules of hydrogen to give us 2 molecules of ammonia. We can also say, which is one of the most important ones that we're going to work with today, we have 1 mole of nitrogen and 3 moles of hydrogen to 2 moles of ammonia. We can take it a step further and we can use a periodic table and molar masses to say that we have 28.02 grams of nitrogen reacting with 6.06 grams of hydrogen to give us 34.08 grams of ammonia. And then considering the law of conservation of mass, we could say we have exactly as much reactants as we do products. Right? All of this can come from just those coefficients from balancing a chemical equation. Oh, later in the year, we're also going to use this as liters as well when we talk about gases. So 1 liter, 3 liters, 2 liters as well. The mole ratios is the most important part for us right now. And here we've got 1 to 3 to 2. And this gives us a total 6 ratios. We can compare nitrogen and hydrogen. We can compare nitrogen and ammonia. And we can compare hydrogen and ammonia. Again, I wrote it both ways because you can see that 1 to 3 is the same as 3 to 1 in this case. You can flip-flop it depending on how you need to line it up in an equation. So let's do an example. Find the mole ratios for this reaction. There are 3 things, aluminum, oxygen, and aluminum oxide. Take a second to think about how and write out in the space provided on your follow-along notes how many and what are all the ratios for this reaction. Pause the video and play it when you think you've got them all. All right, now I think you guys have paused the video, and so at this point you should have written down the ratios that you have collected for this reaction. So here they are. We've got between aluminum and oxygen, making sure to keep those coefficients together. We've got aluminum and the product, aluminum oxide. And here we're comparing oxygen and our product of aluminum oxide. So ratios of how many moles we have, ratios of those coefficients. All right, let's do it for this reaction. There are more things in this reaction. There are 4 substances, so you'll have to have more ratios. All right, so pause the video, write them all out, play it when you think you're done. All right, here we are. We've got iron and water. We've got iron and iron oxide. We've got iron and hydrogen. We've got water and iron oxide. We've got hydrogen and water. And we've got hydrogen and iron oxide. We have connected all of these things. We have made all the ratios we can and made sure to reciprocate it and keep in our coefficients. All right, so these coefficients will be very helpful for us in the next few lessons coming. If you're still unsure about this, you can read the section in the textbook, and I will see you at the next video.